Okay. Good afternoon, everyone who joined us today. Buenas tardes and boa tarde. A trilingual salutation to everyone who made the time to be here with us today. You could be at a plethora of places, but here you are with us, and it's greatly appreciated. That said, today's MTS Houston Section webinar will focus on innovative technologies as we continue to place the emphasis on such technologies that resonate in today's offshore sector. And again, it goes without saying, but it should be expressed. It genuinely is an honor to have you here with us. Moreover, we continue to see webinars as an equalizer, and they have no paywall. So again, this allows for info sharing, the exchange of ideas, and much like we're doing today, to educate, elucidate, and participate. And with that said, we will continue focusing on resiliency, community collaboration, and innovativeness. And the community collaboration aspect is quite key to us in that we've had multiple companies from different parts of the world present, which is really great to us as it adds further color to our endeavors domestically and abroad. So the upcoming webinars, we have Deep Down Inc., which will be focusing on umbilicals for brownfield problems and solutions. And we also have the Bureau of Ocean Energy Management. We have a surprise speakers entitled, and why is BOEM a bit of a topical presenter and company? That is due to the fact that there's a higher impetus for what people are calling the energy transition and offshore wind farms. And the Bureau of Ocean Energy Management, which is part of the United States Department of Interior, is making such push. And again, it does include maritime and offshore technology, so it's quite timely and quite topical. So please come back and join us for those webinars. Now then, our presentation topic for today will be Challenging Convention, Inline Inspection of Unpiggable Subsea Systems. And we have Dr. Cullum, who will be presenting on this. And before we proceed with the actual introduction to Dr. Cullum, we want to add a bit of flavor to the subsea aspect, the offshore aspect of how we're here and why we're here. So it's very key to note that the Marine Technology Society, by way of Mr. Chateau, which is Howard Chateau, is the chairman emeritus of the Dynamic Positioning Committee of MTS. He passed away in 2018, and as it stands, he received several MTS awards, and his offshore contributions continue to live with us. And that ties into the entire subsea aspect of what Dr. Cullum will explain further. And the reason we're able to go into deep water and explore different regions of the world has to do with remotely operated vehicles. And the way we see them today is very different than they were when they first initiated. And Mr. Chateau, if you look at these images here, this would be the genesis of the first, what is arguably the first offshore specific ROV. That's the Mobot. It was used off the coast of California in the 1960s, and it was marinized by the Hughes Aircraft Design and used offshore, again, in California. So what we see a lot with offshore technology and subsea technology is that you have to marinize it. It doesn't just learn to become adaptable at 10,000 feet under the water. There's a lot of engineering and a lot of grit that goes into that, and we'll show what that actually means. So what Mr. Howard Chateau originally created is the Mobot, which you see to the left, and it has a lot of the functions that current ROVs have, which is to be able to interface at the wellhead with the BOP, override, so on and so forth. And now we have the Gemini ROV, which was very recently released. If you see its manipulators, it's greatly advanced, but everything has a genesis, its historicity, and its roots. And the Mobot is just a really great design. And again, Mr. Chateau had a great and strong hand with that. He pursued the neutrally buoyant design, which we won't discuss here. But again, the fact that Mr. Howard Chateau is viewed as the father of dynamic positioning, had a strong hand with remotely operated vehicles, is the reason, again, we are able to explore in deep water depths. And this is just really looking at the history of offshore technology, but also the people who played such a pivotal role. And Mr. Chateau, without a doubt, is such an individual. And as remarked by the drilling contractor, in 1970, he made the industry history with Setco 445, which was the first dynamic positioned oil exploration riser equipped drill ship. And why does that mean a lot to me and to many that may be on here today? I've had the chance to be offshore on drilling and completion projects where you get to see ROVs, dynamic positioning, and all the magic comes together. So I hope this provided additional color to the technology conversation as to who we are as Marine Technology Society and the lineage with which we count on. And without further ado, it is an honor to introduce Dr. Cullum Holton. Dr. Holton is the principal subsea engineer at Quest Integrity. Dr. Holton is a chartered mechanical engineer with more than 15 years of experience in consulting, research, and business development in the oil and gas industry. With subject matter expertise in corrosion fatigue and fracture behavior of pipe girth welds, he has authored and co-authored more than 30 technical papers, and his research is referenced in international assessment standards BS 7910 and DNVGL-RP-F108. Dr. Holton has applied advanced fatigue, fracture mechanics, and fitness for service assessment methods to the design, integrity management, and life extension of pipelines, risers, subsea equipment, pressure vessels, and offshore structures. In his current role, Dr. Cullum Holton provides technical leadership to Quest Integrity's subsea business, which is focused on inline inspections of challenging subsea systems, particularly deep water assets and advanced engineering assessment services. So without any further ado, it's going to be quite exciting to pass over the controls to Dr. Cullum Holton. So Cullum, I will stop sharing my screen, and if you could proceed with yours, it'd be greatly appreciated.
Thanks, Fernando. So hopefully everyone can see my slides now. Yeah, good day, everyone. Appreciate the opportunity to present to you today. Apologize in advance if you hear any screaming children or anyone appears in the background, but it is feed-in time at the zoo. So I attended one of these webinars back in July. It was a presentation that was given by 2H Offshore on riser life extension, and it was a great presentation. Obviously, life extension is driving a lot of our activity in the Gulf right now, and inline inspection was mentioned as being able to provide a lot of useful data, a lot of useful information that can be used for engineering assessments. And then there was a comment that was made, unless the system is unpiggable, and that was left as a somewhat open statement. So after the webinar, I was talking to Fernando, and I thought it would be useful to provide a presentation specifically focused on inspection of challenging subsea systems and dive slightly deeper into what we actually mean by unpiggable. So that's the plan. This is my agenda. I'll talk for about 30 minutes and leave time for questions at the end. So the focus is inline inspection of unpiggable subsea systems. We're going to talk about that in terms of the inspection challenges, but also the technology solutions that we've engineered to be able to overcome many of those challenges. I'll introduce you to Quest Integrity's technology. That's the Invista Subsea ultrasonic inline inspection technology. We'll look at how we deploy that system offshore, detection capabilities. We'll look at some real data. I'll make the case for combining inspection and engineering assessment together. And then finally, I've got a couple of case studies for you, two deep water case studies, one that demonstrates the value of baseline inspections, and another one that looks at inspection campaign economics. So we'll jump right in. So what are the challenges that make a system difficult to inspect, or a term that is commonly used, unpiggable? Well, unknowns, older systems that were never designed to be inspected, missing information, missing drawings, potentially damage or restrictions in the line. Dual or multi-diameter lines, they're challenging. Wall thickness transitions, changes of ID, navigating cladded sections. We regularly have to navigate complex subsea infrastructure, so plets, plems, jumpers, pigging loops if they have one, and then also navigating flexible pipe. We may have to go around reduced radius bends, either topside or indeed as part of the subsea infrastructure, for example, bypass piping. We may have to navigate unbarred T's, Y's, reducers. There may be limited deck space to actually physically maneuver the tool. We often come across short barrel launchers and receivers. Sometimes there aren't any launchers and receivers at all. We may have vertical launchers and receivers. Launching ILI tools vertically and receiving them vertically is challenging. If we require topside or subsea modifications, they can require additional regulatory approval. Physically having the lifting or rigging equipment to maneuver the tool, deep water assets, we're dealing with high head pressures, heavy wall thickness, small IDs. Single line tiebacks are challenging. Subsea tie-ins, what is the diameter of the line that we're dropping into? Where does that line go? Who owns it? And as I said, navigating flexible pipe, even if the focus of the inspection is a rigid pipeline system. So in the end, it really comes down to a matter of risk. So how do we get our tool in and out of the line safely? So they're the challenges. These are some of the technology solutions that we've engineered to overcome those challenges. And I apologize for the wordy slides. It's the most wordy slides. We'll look at lots of pictures after this, but I just want to run through some of these solutions and how we handle some of those unpiggable challenges. So first of all, performance qualification testing. We want to reproduce the inspection challenges onshore in a flow loop to maximize the chance of first run success offshore. We don't want to be doing anything for the first time offshore. Lightweight tools with a small form factor that allows us to hand carry our tools offshore, quick and easy mobilization on a helicopter. It also gives us the means to launch an existing short barrel launchers and receivers, or it makes it a lot easier to install temporary launchers and receivers if no barrels exist. We want our tool, we want our inspection to be minimally invasive. We ideally don't want to make any topside or subsea modifications. We want to be easy to deploy, so hand launch the tools, remove the need for lifting and rigging equipment. We have the ability to launch both horizontally or vertically, and in general, no vessel support is required. Everything's just handled topside. We want to minimize production downtime. That's one of the roadblocks we come up against for inspection. We want short inspection campaigns. The typical tool speed for our system is around 3 feet per second. And our standard operating procedure is to mobilize 2 tools, a primary tool and a backup, to also minimize the chance of any delays offshore. We design tools to be at least 30% collapsible. So that allows us to easily navigate multi-diameter lines and also any known or unknown restrictions that we may come across. Our tools are bidirectional, so we can return to the launch location via reverse flow. That's important either if there's no pigging loop or if an unknown restriction is encountered in the line. All of our tools are untethered. They're free swimming. They follow the flow. They're not pressure driven. So that allows us to navigate unbarred T's. And because we have a very low differential pressure, that means if we do come across an unknown restriction in the line, if it's less than 30%, then we'll be able to navigate it. If it's more than 30%, then we won't get stuck by that restriction. The tool will effectively sit there treading water until we're able to reverse the flow and receive it at the launch location. We can also deploy our tools on wireline if necessary, but they are designed to be free swimming tools. We also designed them for navigating 1D back-to-back bends. That's important for navigating topside piping in order to get into the riser system. We also come across reduced radius bends for subsea infrastructure. We've developed a fleet of high pressure tools. They're specifically focused on deep water inspections where we have high static head pressure. Our system takes two UT measurements. We get a direct measurement of the inside radius and a direct measurement of the wall thickness. So that means that no additional gauge plates or caliper tools are required. We also perform data validation on site. Excuse me. So we check that the data quality is acceptable prior to demobilization. And then this is a question that's come up more recently, but we're also subsea launch and receive capable. So that's a potential inspection solution, for example, for single line subsea tiebacks. So those are some of the solutions, and we're gonna drill down onto some of those in terms of how it actually works. So hopefully you can see this video. I'll just leave it running while I talk over this slide. So Quest Integrity has been developing ultrasonic inspection technology since the 1990s, and it was all driven by a desire to have the ability to navigate and inspect through serpentine coils in fired heaters. So the video that I'm just playing, that's a mock-up of a heater tube. It has our actual tool traveling through it. It's being driven by flow. It's untethered. It's a multi-module tool. And since the development of that initial technology, we've adapted it to inspect several different types of challenging systems. And most recently, we've specialized in deep water inspections. So since 2000, we've inspected more than 4,000 unpiggable or difficult to inspect pipeline systems. More than 100 of those were offshore inspections. If you just look at the upper right image on this slide, this is a temporary launcher barrel that was installed on a deep water platform. So just to give you an idea of scale, you can imagine that our UT inspection tool is inside the red barrel. And the lower image is a rendering of a type of subsea launch system. So in this instance, you could imagine our tool vertically in the yellow portion, and then we would enter the flow line through the Y. Different types of subsea inspection projects. First off, I've listed ILI, inline inspection suitability studies. There's two types of suitability study that we usually get brought into. One is at the design stage, so we're making sure that a new subsea system will be inspectable as part of the integrity management plan, or we get brought in on aging assets, and some of the life extension activity falls under that category, where we're evaluating systems that weren't necessarily designed to be inspected to see whether it is feasible to get an inline inspection tool in and out of the system. Baseline inspections, they are increasingly common. It's called out in some API documents. We use those to establish the as installed condition of the pipeline, and it's often considered the first step of the integrity management plan, almost like fingerprinting the line. And one of the case studies I have at the end will dive deeper into baseline inspections. We then have integrity management programs. So this is regular periodic inspections through the life of field, looking for in-service integrity threats, special inspections or unplanned inspections. This is usually an expedited or emergency mobilization type event. I mentioned at the start of the presentation, we get involved with life extension inspections, particularly riser life extensions in the Gulf. And then also inline inspections in support of decommissioning activities. Okay, so just a few words about the form factor. This is one of the things which allows us to inspect unpiggable pipelines. So we have tool sizes ranging from, we have a fleet of tool sizes ranging from 2-inch all the way up to 30-inch, and we're also working on larger diameter technology. We have single and multi-module tools. So for example, the 2-inch tool is a multi-module tool. We then have single and multi-module tools all the way from 4-inch to 16-inch, and then typically anything above 16-inch would be a single module tool. In terms of tool lengths, anywhere from about a foot long up to around 5 feet in length, weighing anywhere from 2 pounds up to 250 pounds. And the point is that all our tools can be hand carried offshore and hand launched without the requirement for additional rigging or lifting equipment. So that's the small form factor. In terms of data acquisition, what do we actually get? We have tool specification sheets for each size of tool, each type of tool. Generally, our subsea tools, our subsea inspections require custom tools. We collect 100% circumferential and axial ID and OD data of wall loss and geometry anomalies. So if you imagine, so our sensors are offset from the wall, so we get 2 UT readings. We get one reading from the internal radius, and we get a second reading from the wall thickness. And we take those readings every 1/4 of an inch. So if you can imagine a pipeline, this is shown in the upper image, split into 1/4 inch grids, as shown, then we will take an internal radius and a wall thickness reading in each of those grids. So what that means is that depending on the size of the tool, as I said, we have 2-inch to 30-inch diameter tools. Depending on the size of the tool, we are taking anywhere from 2300 to around 18,000 thickness and radius readings every foot. A wall thickness range, anywhere from 50 thousandths of an inch up to 2-inch. That's our qualified wall thickness range. I suspect we could probably go higher than that. So far for deep water inspections, we've got close to 2-inch. We haven't quite hit that 2-inch mark. All of our sensors are calibrated to be within 5 thousandths of an inch of a calibration block. POD is outlined on the tool specification sheets. Typically, we have a POD of 90% for a 1/4 inch squared for wall loss in excess of 25 thousandths of an inch. Our operating temperature is not usually an issue. Generally, we're running offline. So this is driven by the electronics in our tool. It's usually not an issue, but our higher end range is 140F. And then standard technology, anywhere from 1500 to 2500 PSI, still good for shallow water inspections. You can probably get up to around 2500, 3000 feet water depth with standard technology. And then driven by the industry, we developed a fleet of high pressure tools specifically focused on deep water and ultra deep water inspections that are rated up to 5000 PSI. So I mentioned at the start the value of combining inspection and assessment. So we try to do that. So we have software that visualizes and analyzes the data, and then for each inline inspection, we provide a level 2 fitness for service assessment. So each inspection has a level 2 local metal loss remaining strength assessment for the entire length of the line. Usually that's in accordance with an API 579, but any assessment standard can be incorporated into the software. So that's kind of a base level assessment that's delivered with every inspection. Sometimes you may have more complex loading scenarios. You may have more advanced or more severe damage that requires an advanced engineering assessment. So in addition to the standard, we also have the means to export our data or import our data into advanced engineering software where we can perform either more complex assessments or elevate it to a level 3 type fitness for service assessment. Okay, so hopefully this works. It's a short animation. It's not the most exciting animation in the world, but so based on our small form factor, the size of our tool, the weight of our tool, one of the challenging areas that we specialize in is where there's limited deck space and short barrel launchers and receivers. So one example of that is on an FPSO turret. So this is showing we launched in the existing barrel. We're using our single module technology. we're navigating reduced radius bends down through the turret before we get into the riser. So that's one example. Let me just jump to another one. This second example, pretty standard setup for a subsea pigging loop. So we've launched topside, down through the riser, flow line, plet, rigid jumper. There could be wall thickness transitions, there could be clouded sections, changes of ID, through the manifolds, around the pigging loop, and then back on the other side, jumper, plet, flow line, riser, and then receive the tool again, topside. So that's the type of scenario that we get involved with. In this instance, there was a pigging loop. I mentioned earlier that all these tools, you can tell they kind of look symmetrical, so they also have bidirectional capability. So in the absence of a pigging loop, as long as we can manage the flow appropriately, we can launch and receive in the same location. Okay. So let's look at some actual data. So this is the type of data that you would see. So ultrasonic inspection, we get an A scan, we get a B scan, and then what we do in order to visualize is we also turn that into a C scan, and that's what I'm showing on this slide. So a C scan is effectively a 2D representation of the UT data. So we end up with two C scans, one for the inside radius and one for the wall thickness. On this particular slide, I'm showing you a C scan for inside radius data. So if you can imagine that the pipe was cut lengthways, let's say at the 12 o'clock position, and then opened out flat, this is that representation. So inside radius data, you can see this kind of regular variation of kind of blues and greens. That's actually just mil variation in the wall thickness. So the difference between that is probably only a few thousandths of an inch. So this was seamless pipe. We identify all the girth welds. In this particular image, I chose it because there was some counterboring or beveling to improve the fit up at the girth welds. So that very slightly reduced thickness stands out well in our C scan. And then we also pick up on some manufacturing features. So they stand out quite clearly. Actually, in this case, they're all within manufacturing tolerance, but you may still set them up as a monitoring location for your integrity management plan. So that's the type of data that we see. In addition to going in and looking for manufacturing type defects or features, we can also detect metal loss. So uniform and localized pitting type metal loss, both internal and external. So the two examples I'm showing you on this slide. So the lower left image, that is UT data that was obtained in a subsea rigid jumper. This was categorized as CO2 corrosion. That jumper was subsequently pulled, and there was an opportunity to take a photo of that damage. So this is kind of quite a rare opportunity to prove up a subsea inspection where this is the region of damage that was called out in the inspection. And again, you can see this variation of wall thickness. The image on the right, the C scan on the right, this is actually a deep water riser. If you can imagine this flipped vertically, you see the mil variation in wall thickness. This is the girth weld, and then this greeny, yellow, red region, that's external corrosion at the splash zone. So we, for this particular inspection, we ended up with around 24% wall reduction in the splash zone of that riser. Okay, another damage mechanism that we come across more regularly at the moment, or another damage threat that we come across more regularly at the moment is related to acidizing treatment. So there's an increasing number of acidizing treatments used for well stimulation. The acidizing cocktails are HF and hydrochloric acid. They're very corrosive. They need to be highly inhibited to prevent corrosion. So we've been involved in a number of in-service integrity inspections where we are going in after well stimulation treatments to detect for acidizing corrosion and to confirm that the inhibition program was effective. So Again, we have the C-scan, the 2D version on the right-hand side, and then we also have the ability to turn that into a 3D representation of the pipe. So just roll that data back up. This was a deep water inspection. You can see it's a heavy wall pipe, small ID. This is a girth weld, and then we see wall loss on the downstream side of the girth weld. So the well is at this end of the line. The facility is, the platform is at this end of the line. And this is, we've seen this more than once on more than one facility, that if the inhibition is not controlled, then we can see this signature type of corrosion on the downstream side of girth welds related to acidizing treatments. And then, as I said, we detect wall loss anomalies and then also geometry anomalies. So we can detect, obviously, if it's less than a 30% roughly restriction. Actually, for deep water, for our deep water tools, we're often up at maybe 40% collapsibility at our tools. So if we can navigate that restriction, we'll collect the data, and then we can perform an assessment on whether it's a dent or we can detect ovality. And in the extreme, we can import that data into an FE model. This is actually an onshore example. It's a thin wall pipe. We can import that data into an FE model and perform, for example, a dent assessment based on the data collected from the inline inspection. Okay, so we'll finish off with two case studies. The first case study is on the topic of baseline inspections and the importance of data repeatability. So this was an inspection that we actually performed. So it was a baseline inspection that we performed onshore on the stalks in 2016. So we were inspecting onshore prior to this line going into the water and seeing first production. So similar to some of the data I've shown you before, this is one feature that we found in this onshore baseline inspection. We have the girth weld, it was counterboards, we detect that. We can see the wall thickness variation, and then we have this feature here, which was still within tolerance, but was marked as a location, a monitoring location for future integrity inspections. As part of that integrity management plan, we had the opportunity to go and inspect this line again after a period of time in service. So the previous onshore inspection that was conducted in 2016, we then went back and inspected it after a period of production in 2018. So this is the same feature. Don't worry too much about the colors. That's kind of analysts' choice on what they think looks best. But this is the same feature that we found onshore in 2016. We've now inspected and detected it again in 2018. The interesting part of this inspection was this was a bidirectional inspection. So we got to see, we knew we were going to see this line twice. In actual fact, we ended up inspecting this line and gathering 4 sets of data. So what happened here was the first time we ran the line, the cleanliness wasn't quite as good as we desired. So we did a first bidirectional run, we then did some additional cleaning on the line, and then we ran the line again. So as it happened, we were able to inspect this feature 4 times in this particular campaign. So those are the 4 images at the bottom of the slide. So this is run 1 forwards, run 1 forwards, run 1 backwards. You can see we have some data drop out. There was then some additional cleaning. We then have run 2 forwards and run 2 backwards. So we picked up the same feature 4 times, and we were able to analyze that feature, and then we compared it with what we saw in 2016. So what we're looking for is any sign of growth, that feature is actively growing. And in this instance, once you factor in the size intolerance of the tool, this was concluded to not be growing. So obviously we saw it onshore, we knew it was there. We inspected it after time in production, it hadn't grown, and that will just stay there as a monitoring location. So that was where we actually had the baseline data. The definition of baseline inspection is kind of loose. So I've shown an instance where we did it before that line entered service. That's perhaps the ideal scenario for a baseline inspection, but often it's just viewed as the first time you inspect that line. So in this particular project, this was a line we inspected after a period of production. So the line entered service, it produced for a relatively short period of time, then it was inspected, and that became the baseline inspection. So I'm showing both C scans here. So the bottom one is the internal radius. The top one is the wall thickness. So the way we differentiate between internal and external corrosion is if it's internal wall loss, you would see that on the inside radius. If it's external wall loss, then you wouldn't see anything on the inside radius, but you would see a reduction in wall thickness. So here we see no change in inside radius. But we do have a thinner wall in that area. Therefore, that was called as actually pretty significant external wall loss. So that raised a big red flag. When you applied some engineering judgment to this, you looked at the service the line had seen, it actually seemed unlikely that this was an actively growing external corrosion anomaly, but without the baseline fingerprint to compare it to, you really can't be certain. So the plan for this line was, it was obviously marked as a monitoring location. It was then entered back into service for a shorter inspection interval. So the first inspection was carried out in 2018, second inspection in 2019. This is the 2019 inspection. We found the same feature. Again, considering the size intolerance of the tool, we were able to deduce that it wasn't growing. We believe it to be a manufacturing related flaw, and it will be kept in the integrity management plan as a monitoring location. So this just shows that if we'd had that fingerprint onshore, this feature potentially wouldn't have caused the heartburn that it did, and potentially could have avoided another inspection after only a short interval. Okay, these are my last two slides. So this is just another case study. So this was a case study on ease of deployment being the key to regular inspections of deep water risers, and that's one of the things that we're trying to make the case to for industry, that we're trying to make the tools extremely easy to deploy offshore. So this particular example, we inspected 4 ultra deep water production riser flowline systems. They were configured as 2 pigging loops. Water depth was it was actually around 7,500 feet. One loop was around 8 miles long. The other loop was around 11 miles long. The inspection program was part of just regular periodic inspection aimed at looking at in-service integrity threats, but these lines were seeing well stimulation treatment. So there was some interest in looking for acidizing corrosion. In order to navigate these 2 pigging loops, there were several ID changes, wall thickness transitions. We had reduced radius bends on the top side, and then in terms of subsea infrastructure that we had to navigate, we had rigid jumpers, plets, plems, and then also sections of unbonded flexible pipe. So these lines were previously inspected in 2017 by what I've called a conventional UT ILI tool. Topside modifications were required to get that tool in the line. Those topside modifications required regulatory approval. Launcher and receiver barrel extensions were installed in order to accommodate the size of the tool. Rigging and lifting systems were required to lift and launch the tool, and then temporary piping was installed to bypass 3D topside bends, so reduced radius bends topside. The duration of that cleaning and inspection program was 25 days. That included 1 inspection run per loop, no on-site data validation, and 14 anomalies were detected, and then regulatory approval was required prior to returning that asset to service. So in 2019, we ran that with our small form factor UTILI tool. So Because we could fit in the existing short barrel launchers and receivers, no topside or subsea modifications were required. We could fit in the launchers and receivers, and we could navigate the reduced radius bends. Tool was hand carried offshore and hand launched. The duration of that cleaning and inspection program was 10 days. In that period, we ran each loop twice. We validated the data for each loop as being acceptable prior to demobilization. We detected 21 anomalies, including all of those found in 2017. And the final inspection and assessment report was delivered within 3 weeks for both loops. So that's really in a nutshell what we're trying to do for the industry in terms of inspection of challenging and unpiggable systems. So just in terms of the saved downtime alone, we were able to save the client a significant sum of money. And that's really our pitch, is that we're trying to recalibrate the offshore industry in terms of what's viewed as being unpiggable. Why do we want to do that? Well, really the main reason is integrity and reducing risk. So we believe in order to have the most effective integrity management plan, you need to inspect regularly. So if you take, I referred back to a previous webinar on life extension at the start of my presentation. If you take that as the example, if you're able to inspect easily with minimally invasive tool with short inspection campaigns, that encourages more regular inspection. More regular inspection, you combine that with your corrosion modeling, your analysis, we think that produces the most effective integrity management plan. And with that, I will close my presentation. Appreciate everyone's time and listening. My email is on the screen, or Fernando, I'm happy to take questions now as well.
Perfect. Thank you, Colin, for that insightful presentation. So we do have questions that are coming in. And one of the questions that we have is raised by Mr. Bruce Henrici. And he mentions and asked, when you use the term usually offline, does Quest ever use production to push a subsea pig in a single flow line?
So the answer, Bruce, is yes, we can. We do it all the time onshore. We do it kind of in shallow water, and on the export side, it's also possible, depending on the system, offshore. Typically on the production side or the infield side for offshore, we don't. That system will be shut down, and we would run in either seawater or dead oil. We do require a liquid medium for the tool. So yes, it is possible. I would say certainly for our deep water inspections, it's uncommon.
Perfect. Thank you for that, Colin. And I'm receiving different questions, which are in the broader group, chat dialogue, and also direct ones. And this one is one that's in the broader chat dialogue, and that is, what are the minimum and maximum speeds for a good run with your tool?
Good question. It varies by the tool. So each tool will have been qualified to a certain speed. I think I gave a rule of thumb of around 3 feet per second. That's a good rule of thumb for our technology. But another way to think of it is that so going too slow from a data collection point of view is not as bad as going too fast. So if you go too fast, you go beyond the optimum speed, and on the specification sheet we would give you a minimum and a maximum range. If you go too fast, then you're going to miss some data. If you go too slow, then effectively all you'll do is you'll oversample, and we can still handle that data. So anywhere from the kind of 1.5 to, let's say, 4 or 5 feet per second is a typical range. If you drop below that, all well and good. If you go above that, you will miss some data.
Perfect. Thank you. And with that being said, what is the difference between the tool that you utilize, based on what I'm seeing here in the chat dialogue, in terms of having internal inspection versus potentially going with an external type of apparatus via an ROV?
Yeah, good question. I would say the single biggest advantage of going on the inside is we will give you 100% coverage of the line. So if you're able to safely get an inline inspection tool in and out of your system, you will get a picture and 100% coverage of the condition of that line. If you contrast that with an externally deployed tool, they do have some advantages as well. Obviously, you can run those while the system is still producing. To go back to Bruce's question earlier, but the biggest disadvantage is you're really only taking spot checks of the line. So if you know where you have an issue, you know where you want to go and inspect, then an external tool may well be a good tool for you. But to get an overall picture of the line, a comprehensive picture of the integrity of the line, if you are able to get an inline inspection tool in and out safely, then I would say that is a more optimal option.
Perfect. Again, thanks for that. We do have a question here is with respect to the multi-phase, will your tool operate in oil and gas pipelines? And it doesn't provide more detail, but I would presume that to be a multi-phase question.
Yeah, so no, we need well, there's two parts to that question. No, we need a single phase liquid medium, and we can run in different types of liquid medium. The second half of that question is we can and do inspect gas lines as well, but it's usually via a batching type process. So there will be a lead pig and then a column of inspection liquid medium containing our tool, and then a trailing pig. So that might be with something like glycol or MEG that we would run in the gas line, but we do require because it's ultrasonics, we do require a liquid medium.
Perfect. And with that being said, you mentioned glycol, for example, and what would be the benefits to using glycol when doing this type of batch, and why would one use it, for example?
Yeah, really just because you don't really want to put water or oil in your gas line. So it doesn't have to be glycol. We would actually take the advice of the operator on what medium they would prefer to put in their gas line. It's really dealer's choice on that.
Perfect. Thank you for that. And when you're running in an infield line, and what I mean by that is, based on this question I have, is the picking loop. What challenges do you see when you're going in through the actual manifold and have to go through the pigging loop? Because one can envisage changes in the internal radius. So how does Quest approach that?
Yeah, so the main challenges that you would see are changes of wall thickness, changes of ID, whether that's related to just changes of the steel wall thickness or having some cladded sections, be that the jumper or a cladded line, and then also a reduced radius bend for the pigging loop. So they're the challenges that we come across. They're really overcome by having a tool with high collapsibility. So as long as you have a tool that is offset from the wall and can collapse as you go through a restriction, then it's relatively easy to navigate those types of features. And maybe I didn't draw that out enough in the slides, but effectively what you have is, if we say that we have tools from 2-inch diameter up to 30-inch diameter, because each of those tools has around 30% collapsibility, then they can inspect up or down a diameter of pipe. So if you imagine that each one of the tool sizes has the same hard body, and then it's trimmed to the system that we're inspecting, either via discs or brushes, and we can trim those discs or brushes to ensure that we're able to center the tool correctly in multiple diameters. So absolutely, the smaller change of ID, the better. But if we need to go up or down a pipe diameter, then it's certainly doable.
Perfect. And that brings the next question is with respect to, you mentioned discs and brushes. How does your tool actually work, and how does it work in a multi-phase line where you might have paraffin or asphaltene, for example, and how does that inspection get also carried out? I know there's two parts to that, but just reading what I'm seeing here.
Yeah, so I mean, this is an ultrasonic technology, so we need a relatively clean line in order to receive the UT signal back. So all of these projects go through what we call a progressive cleaning program prior to putting the UT tool in the line. And we would look at records available on those lines. There may be a form of chemical cleaning. Typically, it's a progressive cleaning program with a range of cleaning pigs that get progressively more aggressive. So you would, for example, start with a foam pig. You would then perhaps go to a brush pig. And then once you analyze the debris that's coming out of the line and we think it's clean enough, we'll then run the UT tool. The way our UT tool works is it's almost neutrally buoyant. So if you put it in a liquid filled pipeline, it will sit there, and then it's trimmed with brushes and discs as the point of contact. So what you're trying to do is you're trying to center that tool in the line. The key is to have it centralized in the line, so you have a straight shot to shoot your UT signal and receive it back. So I think they're the two aspects of that question.
Awesome. And I have another question, which is three parts. And the way it's come in, I'll read it verbatim. How much power do the ultrasonic sensors use? How much power is carried in the batteries? And related, what is the maximum deployment time for the sensors? And I'm glad to explain or read any of these questions verbatim once more, because they are threefold.
Okay, so we generally use a nickel metal hydride battery. The life of that is around 7 or 8 hours. The benefit being that it's also rechargeable. We can also use single-use lithium batteries, which can double the life of the tool. There's other ways around battery life. So for example, when I talked about single and multi-module tools, one option is to add an additional module to the tool. So you would potentially add around a foot to its length, but you could add an additional battery module in order to increase the runtime of the tool. And it is just a battery operated tool. It stores the data locally, and then once you take it out of the line, then you download that data. Another method for overcoming the challenge of battery life when you're inspecting very long lines is it requires multiple runs, but you can set it up that the tool inspects the line in segments. So obviously we're calculating, most of our tools have odometers, we're calculating the flow, but we can set the tool up that it won't turn itself on for a certain period of time. So in simple terms, if you had a line that was too long for a single battery run, you could inspect the first half of that line. You could then go back in, inspect for a second time, but not actually activate the tool until you reach the second half of the line.
Perfect. That works. And with respect to the odometer and measuring your speed or where you're going, how do you know when you're in the vertical and horizontal position?
Yeah, so it's a good question. So we have an odometer, we also have an IMU, but the IMU only tells you which way up you are when you're running horizontally. So that kicks in again when we come out the bottom of the riser, but in order to know when we're in the vertical section, we do have to look for points of reference and post-calibrate that after the inspection. So the two challenges that you usually come across for a riser is obviously your vertical. So if you can potentially have overspeed issues. We typically don't have overspeed issues because we're driven by the flow, not the pressure. And then the IMU doesn't know which clock position is which. As soon as the tool is running horizontally, then the IMU does know the clock position.
And for those that are joining us, could you expand further on what an IMU is, just so I know we tend to use acronyms in the industry, but just so everyone's level set.
I
That
can't
may not.
remember what it stands for, Fernando, but it's similar to what you have on your phone, where you turn it and the screen changes to the direction that you've turned your phone. Is it an inertial measurement unit? I'd have to look it up.
No, perfect. And I know in the offshore industry, we tend to have more acronyms than words in the dictionary.
Yeah,
So,
that's not an offshore acronym.
well, I've used it, I've heard it in offshore sense, but here we go. Inertial measurement unit. Thank you for that, Mr. Martin. He's been quite well, and
Thank you.
he's the individual who raised the three-part question. So,
Excellent.
Martin, I don't know you personally, but being that you've been quite engaged by sending these direct questions, do you have any statements or questions to add to Column? Or if not, I can come back to you and read one that I've already received. And with that said, Column, is when it comes to the barrels and the receivers, how do you prepare for that for projects? And what do you see as an obstacle in that space?
Yeah. So the first step in all of these projects is obviously we want to understand what infrastructure our tool is going to have to travel through. So the first step in this is getting the drawings, and that would include all of the dimensions, the lengths of the minor barrel, the major barrel, the diameters of any existing launch receiver barrels that are on the platform. Based on that and which tool we would recommend, we would be able to evaluate whether we have a tool that fits in the existing infrastructure. If we don't, one option is that we can supply temporary launchers and receivers, and that was one of the images that I showed during the presentation. But in general, the first step would just be to get eyes and evaluate the drawings.
Perfect. Thank you for that. This is a great question. Waiting to see if Martin will come with another question. If not, very pleased to go to the next one. And how does Quest Integrity view the life extension space in terms of the current offshore climate?
I mean, life extension is very active in the Gulf right now. As we understand it, the riser life extension is being treated similar to riser design. So you would also need a third-party CVA to be involved. And that process, that includes a hindcast assessment and a forecast assessment and a forward-looking in-service integrity plan. And that's really how Quest looks at this. So our view, as I made at the end, is it's better for more regular inspections. So there's two ways that you can look at the life extension. Should you be going after, a 10, 15, 20-year life extension and trying to match the inspections that you're able to do onshore prior to that asset entering service? Or should the goal be to inspect more regularly? If you do that, then the capabilities of the inspection tool doesn't necessarily match what we can do in the shop onshore, but you take a more regular look at the condition of your facility. And that's really my view of the best way to go. The caveat to that is, in order to take that approach, you need to be able to get your inspection tool in and out of the line quickly and safely. If you can't do that, then you always come across a reluctance to inspect. If you can make the inspection easy during a standard shutdown, then I think that would be my pitch for riser and pipeline life extension, is more regular inspection.
Perfect. Thank you for that, Colum. And we're now coming to the 1 p.m. mark, which is bringing us to the conclusion. But before we do so, and I'd just like to give a great moment of appreciation for Dr. Colum and others who have presented and have graciously given their time to do so. And that said, I'd just like to conclude with trilingual salutation and conclusion at this point, which is muchas gracias, muito obrigado, and thank you. So for everyone who made it, again, please tune in as we will be having additional webinars. Once again, thank everyone. Bye-bye.
Thank you.